Welcome, guys. Hope you all are doing great. So, today we're going to be uploading our YouTube video Advanced Level Northwest Mock 2016 Part 4. The question says two air-cooled capacitors of capacitances C1 and C2 that have the same area of overlap but different plate separations are connected in series with a 2-volt power supply as shown in the figure below. If the plate spacing of capacitor 1 is 5 millimeters and that of capacitor 2 is 7 millimeters, calculate the A potential difference across each of the capacitors when the switch is closed, and B the total energy stored in the capacitors if C1 equals 2 microfarad.
Okay, Pooja, thank you so much for that smooth reading. So the A part of the question says potential difference across each of the capacitors when the switch is closed. All right, so what we're going to recognize here is that we can also use potential divider rule for capacitors which are in series in a particular circuit across a particular EMF source. How do we do that? Well, so that's part of our question analysis, okay? So like we see, so capacitor in series has potential divider rule. However, since the PD across a capacitor has an inverted relationship with its capacitance, you can see this from your invoice CD. Right? So V and C have an inverted relationship because C then becomes Q over V. The potential divider rule for capacitors is as thus. So how do we know how much of this EMF is dropped across each one of these capacitors? It's what we do. So the voltage that is dropped across C1 is rather C2 divided by C1 plus C2. Why? Because capacitance and voltage have inverted relationships. Okay, good. And then the PD that is dropped across V2 or across C2, which is V2, is rather C1 instead, capacitance of these other capacitors divided by C1 plus C2 times E. So that's how the EMF is shared between those two capacitors. Now, what we can do is that we can also calculate capacitance by the permittivity of the medium between the plates multiplied by the area of cross section of the plates divided by the separation of the plates. Okay, so V1, that would mean that, well, in place of C2, I can replace this expression for what C2 is. So we get the permittivity of that medium. Remember that it's an air-cooled capacitor. So if it's air-cooled, it means that the permittivity there is basically that of free space, right? So cross-sectional area over D2. You do the same for C1 and then do the same for C2. Now notice that the permittivities are the same. Why are they the same for both capacitors? Because they have the same substance in between their, or in the area of overlap of the, Jesus, messing this thing up. So they have the same substance in the area of overlap of their plates, right? So, and that substance is air. So because it's air, then they have the same permittivity, and that's why you have E here and you have E for both C1 and C2. So if we get that math and we simplify that, you notice that EA, we can factor out EA up here, factor out EA down, and then we strike those off. So we have left with 1 over D2 over 1 over D1 plus 1 over D2 multiplied by E. So that simplifies to we know D2, right? 7 millimeter. I'm not converting that to meter. Why? Because we recognize that the result here is independent of this result of this particular unit here. This is meter up, this meter down. So those, they are going to ratio off and go off. So I don't need that. So yeah, that's why I just keep it millimeters. Okay. So if we do that, then we simplify, we get 0.83 volts. Do the same for V2. Here we just basically have to do what? 1 over D1 instead, right? So all of this work that we've done for V1, we just basically copy the same thing to get V2. So when you ratio that, you realize that our V2 is 1.2 volts. So guys, we've gotten the PD across C1 and C2 with just the fact that, well, we can use the potential divider rule like this, then the capacitance are expressed like this, and then we simplify, and then the rest is just math. That's it, right? So the next part says the total energy stored in the capacitors if C1 equals 2 microfarad. Now you need to get C2, okay? So how do you get C2? Well, now since C1 is EA over D1 and C2 is EA over D2, if we ratio C1 to C2, we're actually going to get D2 over D1. So just ratio these two things like that. EA will cancel out, and then you get D2 over D1. Now, what that means is you are going to make C2 the subject from here. So our C2 is going to be D1 over D2 times C1, all right? So when you put in what D1, D2, and T1 are, you realize our C2 is just 1.4 microfarads. Again, that's just math. Now, when you get that, our E total, the total energy stored by these capacitors, basically the sum of the individual energy stored by the individual capacitors. And so how do I calculate the individual energies? Well, it's half CV squared. So E1, which is the energy stored by capacitor 1, would have half C1 V1 squared plus half C2 V2 squared, right? For E2. And so we keep plugging what C1, V1, C2, V2 are. The rest is just your calculator and maths. So E total is 1.7 microjoule. And that is it, guys. So that is what you had to do about this particular question. I hope you really got what we're doing. And if you have any doubts anywhere, you can feel free to drop it as a question in the comment section. I will reply to any of our comments. So yeah, feel free to drop them down there, right, Bridget? Yeah. All right, shy girl, it's not talking. All right, guys, thank you so much for checking out.